QR decomposition, how Gram-Schmidt gives an upper triangular matrix. So reviewing our Gram-Schmidt, starting with a vector, I just scale it for unit length. If I have two vectors, I subtract projections and get an orthonormal basis F1 and F2, and then the hard one, three vectors, subtract off projections, orthonormal basis 1 through 3. And the scalars were the inner product against the input vector. Which gives a nice clean decomposition. Recall geometrically, this is then the projection of V3 against F1, the projection of V3 against S2, and the projection of V3 against F3. These inner products are scalars. Let me just give them a name. Instead of having to write the inner product, well, let me just call it capital R. And I'll just keep track of what I'm doing by the indices, just to kind of get the notation ready. And yes, this is foreshadowing the structure of the R matrix with the indices transposed for the matrix. Now to know how vectors work, we want to rewrite the vector manipulations as transformations. In particular, so if I have a vector, I can think of it as a transformed standard basis vector. So we're going to do a change of basis on the output, and that'll generate a new matrix taking input to output. So our Gram-Schmidt, there's our new basis. So E1 goes to F1 with a change of basis, and the linearity preserves the constant. So our first column is F1, and that scalar of E1 is the first column of the new matrix. Now I'll do the same for V2. It's a transformed E2. My projection coefficients with the blue and black transposed. But this is then F1 and F2 are transformed E1 and E2. Second column of matrix. Putting in the constants, second column of the matrix. Now let's do the same for E3. Let me break it down a little slower. So V3, transformed E3. When I feed E3 through the transformation, it's going to be a series of constants times the basis vectors. Those constants will be the column of the matrix. By Gram-Schmidt, it's our projection coefficients applied to F1, F2, and F3. F1, F2, F3, the F's are transformed standard basis elements. Linear combinations are preserved, and those constants become the third column of my matrix because it's where the third basis vector goes. So there's my R matrix and my Q matrix. Well, if it's good for the basis elements, it's good for anything that can be made from the basis elements. So given any vector x, gives me Tx. Feed it through the other two, and there's my QR decomposition.